Hi guys, welcome to our new lecture on 8085 microprocessor. In this lecture, we'll be covering the architecture of 8085 microprocessor. In the previous lecture, we had already covered the introductory part. So let's go into the architecture of 8085 microprocessor. So in the left, we can see the block diagram of 8085 microprocessor. That is the basic architecture of 8085 microprocessor. So learning the architecture, looking at the diagram, it might look very difficult to learn, but there is a very easy way to learn this architecture. The easiest way is that you learn the architecture in a proper sequence, the sequence in which the processor works. So here in the previous lecture, we had already seen what is the sequence in which the processor works. There is only one sequence in which the processor works. It first fetches the instructions from the memory. It decodes. In the right, I have already written it over here. The first process the microprocessor do is fetching of the instruction from the memory. Then it does the decoding of the instruction, and finally it does the execution of the instruction. So if you look at the sequence and if you learn with this sequence, the architecture is going to be pretty easy for you guys. It's a very simple architecture that we have for 8085 microprocessor. So let's get started. So the first function of a microprocessor is fetching of the instruction from the memory. For fetching the instruction from the memory, you first require the address. Now, where is the address? The address is in the program counter, right? Program counter is a 16-bit register, gives the address of the next instruction to be fetched. So program counter holds a 16-bit address of the next instruction that has to be fetched. So once you have the address, you can start from here. The program counter is a 16-bit register which holds the address. The program counter gives the address onto the address bus. Here is the address bus. You can see it over here. This is the address bus. You can see the address buffer. There are two address buffers, address and data buffers. Here it is written, I think it's not pretty clear. It is A8 to A15 and this is AD0 to AD7. Right now let's look at A0 to A7. D0 because this address and data bus, they are multiplexed. These 8 bits or these 8 lines are multiplexed. It is written as AD0 to AD7. The same set of lines or the same set of physical wires are used for address, putting the address as well as for taking in the data. So that's why it is given as AD0 to AD7. So once you have the address in the program counter, it is given to the address bus, and the address bus goes directly for A0 to A7 and A8 to A15 16-bit address bus. It goes directly into the memory. It goes into the memory. It locates the memory location where the instruction is present, right? From there, the instruction is fetched through the data lines, So here it is fetched back through this data lines. There is a difference, right? The address bus is only used for putting the address. Now data bus is used for taking in the data. The instruction comes into the microprocessor as a data. So it comes in through the data bus, it goes through this bus and comes to the instruction register. So don't forget the sequence. Program counter has the address, goes into the address bus, goes to the memory, takes the instruction, comes back, goes into the instruction register. Now instruction register will store the instructions. Now the instructions are in the form of zeros and ones. We already saw all these things in the introductory lecture. The opcodes are the combination of zeros and ones which represent the instructions in the machine language, will be stored in the instruction register. From there it goes into the instruction decoder. You need to make sense out of these opcodes, right? And to understand them and act accordingly, the processor has to understand them. So each sequence has a prefabricated circuit and it goes into the instruction decoder and it understands what is the operation that has to be done or executed, and then it goes into the timing and the control circuit. Now timing and control circuit generates the timing and the control signals for each and every part of the processor. Now let's say if you want to add 2 registers, it will give the information that 2 registers has to be added, namely let's say you want to add the accumulator and the C register. So it will give the information that the data from C register and the data from accumulator has to be released, and the ALU, in the ALU it is going to add these 2 values. Now arithmetic logic unit, right? Arithmetic and logic unit, it from the name itself it is very clear, it does arithmetic and logical operations, right? Now this is where all the processing takes place. Let's say your arithmetic operations, addition, subtraction, multiplication, division, or logical operations, all the such kind of operations will take place in arithmetic logic unit, ALU. Now here you can see the ALU is connected to accumulator and there is a temporary register. Now temporary register can take data from any of the registers over here, or it can take the data from the memory, right? It can take data from any place. Accumulator is always fixed. Always your first operand will be in your, should be in your accumulator. If you want to add 2 data, or you want to subtract, or you want to multiply or divide, any operation you want to do, the first operand should always be in your accumulator. Is that clear? So whatever operation you want to do, the first operand should always be in your accumulator, and the second operand can be put into the temporary register. Now this register is not accessible to the user. Whatever register you chooses to add with the accumulator, automatically the data goes into the temporary register. It is done internally. You have no access to this temporary register. The data, whichever data you want to add, will go directly into the temporary register and will be added with the accumulator, right? Now in 8085 microprocessor, accumulator is the first operand, as well as the result also goes into the accumulator. From here it goes into the arithmetic logic unit. The data, the second data will also come to the arithmetic logic unit. The result comes back to the accumulator. Always in 8085 microprocessor, the accumulator stores the result as well as the first operand. Now there is another register called flag register. Now flag register will store the status of the result. Whatever operations you do, the current status will be stored in the flag register. Now we'll be looking at the flags, different flags like carry flag or 0 flag, all these flags in detail in the coming lectures. So it stores the status of the result. Status of the results means, let's say you are adding to 8-bit numbers and you have a carry out, which means you are getting a result of 9 bits. So there is a carry, right? So if there is a carry, the carry flag will be set to 1. A very simple thing, right? Now this flag register will be updated with each and every instruction. It holds only the current operation, arithmetic operations result. So it gets updated with each and every arithmetic operation. So that is the simple architecture of 8085 microprocessor. Now along with accumulator, I think we haven't discussed some of the other registers. There are some few other registers over here. This is B register, this is C, this is D, this is E register, there is an H and an L register, right? Accumulator, I hope everybody knows from the name itself, it is very clear. It accumulates the data. Whatever result that you get will get accumulated into your accumulator, and it is the first register that is always used in any arithmetic operation. Then there are some general purpose registers. General purpose means you can use it for storing any random data that you want to store. As a programmer, you can store any random data in all these 6 registers as well as your accumulator. 7 registers are there for putting your data. These are also called general purpose registers. Even though accumulator has a special function of accumulating the results, still they can also be used as general purpose registers. Now B is a 8-bit register. All these registers are 8-bit registers. B, C, D, E, H, L. All these registers are 8-bit registers. There is also 2 more registers, W and Z. Now these 2 registers are not available to the user. It is only available to the microprocessor for putting some temporary data. That's why it's called the temporary register. Now we won't be learning about these registers because we can't use it. As a programmer, you have no control over these 2 registers, so we won't be learning these 2 registers. It is exclusively used only by your microprocessor. Now B, C, these 2 are 8-bit registers. They can also be used as a register pair of 16 bits. You can use B and C together as a 16-bit register, where B holds the higher 8 bits and C will hold the lower 8 bits. Similarly, DE can also be used as 16-bit registers. HL can also be used as 16-bit registers. Now it is your wish how you want to use it. Either you can use it as 16-bit registers, or you can use them individually as 8-bit registers. I hope it is clear. Now HL has a very specific function also. These can be used as general purpose registers, but they are used for pointing to the memory locations in the memory. These registers will hold the address for pointing to the memory. So that is a very special function of HL register. Then comes your incrementer and decrementer. Now your program counter has to be incremented after the fetching of the instruction. I hope that is very clear, because you will write the instructions in the memory in a sequential manner. So once you fetch one instruction from the memory, you will have to increment the program counter so as to fetch the next instruction from the memory. So these the program counter is incremented using this incrementer decrementer address latch. So now there is a very specific question that arises with this incrementer and decrementer. When is the program counter exactly incremented? Whether it is after the execution of the current instruction, or is it side by side of the execution of the current instruction, or is it before the execution of the current instruction? Now the answer is very clear. In many sources you might see that the program counter is incremented after or side by side with the execution of the current instruction. In many textbooks you might see this answer, but that is not true. The program counter is always incremented before the execution of current instruction. Before execution is the program counter always incremented. This is a very important point to be noted, because many of the students get it wrong, and this has a very important application while writing programs. Whenever you use your jump instruction, if you have to give a relative address, this is going to be very much handy. This point is going to be very much handy. So you need to be very clear about this. Program counter will always be incremented before the execution of the current instruction, because when you give relative addresses, this is a very important point to be noted. Now comes your stack pointer. Stack pointer stores the address of the top of the stack. Now what is a stack? Stack is a set of memory locations. Now you can see stacks in various parts, in various applications. Let's say your WhatsApp. Now I hope you know what is a stack. Last in, it functions in the form LIFO. Last in, first out. Whatever comes in last will come out first. Whatever you put in last will be shown in the first. Let's say your Gmail, whatever mail you get in last will be shown in the top of your application. Or your WhatsApp also has whatever messages you get in your WhatsApp will be shown at the top of your WhatsApp messenger or your messenger. Like almost all the applications that you use today in your mobile or in your laptop or in your PC, all of them work in the form of a stack. your call logs or your WhatsApp messages or your normal messages, your Messenger, your Facebook, all these applications works in the form of a stack. Now stack is stored inside your memory. Now certain part of your memory can be defined as a stack, and the stack pointer will always point to the top of the stack. It will always point to the top of the stack. Stack grows backward. In 8085 microprocessor, whenever you put in data, what happens? There are two operations for putting in data. There is a push operation, and a pop operation. Push stands for putting in data into the stack. Now whenever push operation is performed, what happens? The stack pointer will be decremented and the data will be stored into the memory location. Now there is a difference in 8085 and 8051. In 8051, when you give a push operation, the stack pointer is incremented, but here the stack pointer is decremented when you give the push operation. So stack grows backward in 8085 in the memory, but for 8051 microcontroller, it is the opposite. It grows in the forward direction. It goes from 07 to, in the internal RAM, it goes from 07 to 08, 09, like that. But in 8085, whatever memory locations you define for stack, from there it goes backward. Let's say you have defined 5000, then it goes to 4FF, yeah, it will go 4FFE and so on. So that is how the stack will go. I hope that is clear. So stack pointer will always point to the top of the stack. Now you have is called the multiplexer. I hope you know what is a multiplexer. Multiplexer is a device that is used to reduce the number of lines, the number of wires for data transfer. Let's say you have a lot of data, you can transfer all the data using one wire by using the select lines. At a time you can send only one data. So from all these registers you can send all the data using one set of wires using the select lines. So whichever register has to be released, depending upon that, the select lines will choose the data from those registers, and it can be sent through this multiplexer. So I hope then you have your timing and control block. It generates the timing and control signals for each and every registers, or even for each and every operation that has to be performed. And then you have your interrupt control. Interrupt control we'll be discussing in detail. There are 5 interrupts: INTR, RST, 5.5, 6.5, 7.5 and trap, and there is another signal called interrupt acknowledge. So all these interrupting signals we'll be learning in detail in another video lecture. So this is the interrupt block, and there is a serial IO control, serial input output data. There is 2 pins, serial input data, serial output data. This we'll also be covering this in a detailed lecture, because this covering these 2 portions will make the video much larger in size. I mean the time will be very much more, and it is not advisable to learn these concepts right now unless you are done with other basics of this 8085 microprocessor. So this is the basic architecture of 8085 microprocessor. I hope this is very much clear for you guys. Anyway, once again we'll go through the sequence and the architecture once again quickly. We'll do a quick recap on the architecture of 8085 microprocessor. So we already said that it is always good to learn the 8085 microprocessor architecture in a very proper sequence. The first function of microprocessor is fetching the instruction from the memory. For fetching the instruction, you need the address of the instruction and in the memory. 8085 has a 16-bit address line, right? So what is the maximum memory that can be connected to 8085 microprocessor? It is 2 to the power 16, which is 64 kilobytes. I hope that is very much clear. We have already discussed all these things in the previous lecture. So it can connect up to a memory of 64 kilobytes, 2 to the power 16, because we have 16 address lines. From the memory you get the instruction, the exact location of the instruction using the program counter. The program counter will give the address of the next instruction that has to be fetched. So we'll put out the address onto the address bus, and the address bus will locate the memory location in the memory. From there it takes the instruction through the data bus, right? It goes, the fetching happens over here, it fetches the instruction through the data bus, it goes into the instruction register. Then it has to be, next step is it has to be decoded. Instruction decoder block is going to decode this instruction. It will make sense out of this opcode, the 8-bit opcode that we have, a set of zeros and ones. It gets decoded over here, and then it goes into the timing and the control block. The timing and the control block will generate the signals for the execution of the instruction. So execution mainly happens, most of the instruction gets executed in the ALU. If you have an addition operation, subtraction operation, or any kind of arithmetic operation or logical operation, everything will happen in the ALU, arithmetic or logical operations. So you have an accumulator for giving the first operand, and then there is a temporary register which can take the data from any of these registers, general purpose registers like B, C, D, E, or H, or L, or it can also take the data from any memory location, right? So this data, both these datas will come onto the first data you have to put onto the accumulator. Second data you don't have to put it into the temporary register. The temporary register will automatically get whichever data that you are giving from any of these general purpose registers or from the memory, right? And then both of these data comes to the arithmetic logical unit, and with the operation that the instruction has, or the combination of opcode has given, the operation corresponding to that opcode will be performed by the ALU. The status of the result will be directly put into the flag register. Status in the sense the sign of the result, or the if there is a carry out from the result, all these datas will be put into the flag register. We'll be discussing the flag register in detail, which are the different flags of 8085 microprocessor. And the result will go into your accumulator, right? And then we have already discussed there are 7 general purpose registers, including the accumulator. B, C, D, E, H, L, these registers can be individually accessed as 8-bit registers, or they can be accessed as a pair of 2 registers. You can either take B and C together, D and E together, H and L. Only these combinations can be taken together. You can't take B or B and E together. No, that is not possible. These registers can be taken as a pair of 16-bit registers. B and C together forms a 16-bit register. D and E together can be formed as a 16-bit register. H and L also together can be formed as a 16-bit register. Or you can use them as individual registers of 8 bits. Now H and L has a specific function of pointing to the memory locations. So these 2 registers together can form the address of any memory location from where you want to take some data. So we'll be learning those in the coming lectures. Then you have your stack pointer. Stack pointer will point to the top of the stack. In case you are using stacks for your program, if you want to put data into stacks, you'll be using the stack pointer to point to these datas and take these datas out of these stacks. And then we have already discussed all these things, I think. Then you have your interrupt control and serial IO control. We'll be discussing in detail. Basically this is for managing the interrupts. There are 5 interrupts: INTR, RST5, RST6, RST7.5, RST5.5, 6.5, 7.5, and trap interrupt. There is also a signal called interrupt acknowledge. That's for acknowledging the interrupts. So we'll be discussing this interrupt part in detail. and then you have your serial I/O control. For serial I/O control, there are two pins: serial input data, serial output data. So we'll be discussing those also in detail in another lecture. So till then, thank you for listening to this lecture. Have a nice day.